Well, hello. Hey, today we're working on two topics combined into one. They really do relate well with each other. We're going to look at the extreme value theorem, which will help us identify absolute extrema. So let's get started. Previously, we used the first and second derivative test to locate local extrema, like relative mins and relative maxes. However, those don't always find the absolute max and mins for us. So that is our task today. You can see by this graph that we have an absolute max at A, but down here at B, we pick up both a relative min and a absolute min. So they can be one and the same. It's worth noting that I got to make a correction. This says minimum. That point B is both a relative min and a absolute min. Then we can guarantee you that there will be an absolute min and an absolute max. It's the only way possible to draw a function, right? If it has endpoints, it can do whatever it wants, but at some point it's going to begin and end, and there's clearly going to be an absolute max and an absolute min. Every theorem has a condition or multiple conditions. In this case, we had two on ours. We can only apply the theorem if the conditions are met. We've been working with that. If the conditions are not met, then we cannot apply the theorem and we must consider another approach. For the EVT, what are those conditions? Well, you need continuity and you need a closed interval. If the conditions are met, what will you be guaranteed? That the function will have, without a doubt, an absolute min and an absolute max. Not an or in there. It's a strong and. We will have both. Remember, this is what we call an existence theorem. It tells us they're going to be there, but it does not tell us how to find them. The other two existence theorems that we've encountered was the mean value theorem as well as the intermediate value theorem. Okay. Now, complete the table listed below of the following functions. Is this function continuous on the closed interval? Well, it certainly looks like it, doesn't it? It is continuous, and I see endpoints. Can I apply the EVT then? Absolutely, we met the conditions. Does the function have an absolute max and an absolute min? Yes. And then make a statement about it. Well, this was our absolute max. This was our oops, not there. Excuse me. This is our absolute min. And this was the max. All right, so I would say that absolute max is height of 3 at x equals -1. Absolute min is, what is it, -1, and it occurs at x equals -3. The next middle function there is f continuous on the closed interval. It is continuous, but we don't have closed interval. Not closed, right? So this would have to be a big fat no. Can I apply the EVT? No. Does it have a max or a min? Yes, it does. It actually has a min. That min, we'll call it right there, absolute min. And we have absolute min is -3 for its y value, happening at x equals -1. So the EVT didn't come into play, but yet we still had an absolute min. EVT, if it would have been applied, if it could have been applied, would have guaranteed us both a min and a max. All right, this next one, is it continuous? Absolutely. Is it closed? Yes. If you want, maybe even circle these two items, because those were what we were looking at. Can we apply the EVT? You betcha. Does it have an absolute max and an absolute min? You betcha. And where are those at? Absolute max has a height of 4. Is 4 at x equals -3? And don't forget there's two of them here, and x equals 3. We got a max and we have a max. Okay, absolute min is height of 1 there, isn't it? This is our min. Is 1 at x equals 1, and there's only one of them. Okay? Now let's get into some where we don't get the nice graph to work from. Bomb. Candidates test for absolute extrema. So these 5 steps are kind of the procedures we will walk through to come up with the absolute mins and maxes. First thing we're going to do is find critical values. Then we'll create this table that includes those critical values as well as the endpoints. Just a note here, critical values. How do I get critical values? We just studied this. F prime of x equals 0 or undefined, right? That's how we get those. When finding the absolute extrema, we'll plug the x value back into the function equation to get our y value. This gives us the y value, which then allows us to judge which one is highest and which one is the absolute lowest. The greatest value is the absolute max, and the least value is the absolute min. Give the absolute min or max using the following wording. So when I make a statement about it, I can say the absolute max is this y value at a location of x equals. Same is true with absolute min. Another thing to note, this is important. There's many ways to ask for an absolute max. You could say, what is the absolute max? What is the global max? What is just plain old the maximum? That we interpret as global absolute. The only way to get a relative max is to use the word relative or local. Okay, so I never will be confused when the AP states maximum, which they often do. I have to interpret that as absolute. How do we do these? Well, we're going to follow the protocol set forth in that candidates test for absolute. First thing it says is find critical points, then we'll create a table. So let's do it. Critical points. I'm just going to kind of make a note here. That's what I'm after. I need f prime. F prime equals 0 or undefined. Well, since it is a polynomial, I don't think there's any chance there's going to be any undefined points. 4x minus 8, factor out and 4 just to help us get to where does this equal 0? Obviously, x equals 2. And then we know we have endpoints, don't we? What are our endpoints? 0, I meant to write x equals, and x equals 3. Now let's come in with a candidates table or candidates list. And I like to list them out kind of least to greatest. So x equals 0, x equals 2, that one's coming from the critical point, and x equals 3, the endpoints. So now how do I determine if there's where the absolute max and min occur? I need to take it back to the original function, f of 0, f of 2, f of 3. Let's get some y values now. 0 goes in. I'd have 0 squared times 2 is 0, minus 0, plus 1. Looks like we get 1. 2 goes in. 4, 8, 8 minus 16 plus a 1. You probably can't see my eyes, but I'm looking back there. And negative 8 plus 1 is a negative 7. Can you calculate out the 3? When 3 goes in, it comes out to be negative 5. Trust me on that one. All right, absolute max. Absolute max is 1 at x equals 0. Absolute min is negative 7 at x equals 2. They really aren't hard to do, but I can tell you what the AP is looking for. They are definitely looking for this analysis. They also are looking for you setting equal or finding undefined. So it is important that you write this stuff out. Don't take shortcuts. You will lose points taking shortcuts. You will lose points from me. You will lose points from the AP. B, we have C and D to go. I have the answers for D there. I'm not going to walk through that one with you. C, we should do this one. It is a quotient rule, so of course we've got to do the derivative of h prime using quotient rule. If you are one that has a hard time deciding, Write it down. How did I get this derivative? Derivative of the top times the bottom minus derivative of the bottom times the top, all over bottom squared, no derivative of the bottom, just bottom squared. All right, let's simplify this out. I've got 2x squared minus that x squared, give me an x squared. I have 2x plus multiplied times a positive 3 would give me a plus 6x. That's over an x plus 3 quantity squared. Factor out an x, I would have, you know what, I'm going to have to come down to the next line anyway. I'm going to say 0 equals, factoring out my x, I'd have x plus 6 over, right? Put a little bit of thought process into how you're organizing your space, your workspace. It has to be such that people can follow your work and your logic. Next, I'm going into the candidates test. And for that, I am going to list out all of my candidates, which I guess I didn't complete, did I? So off of this, we get x equals 0, x equals negative 6, and from the bottom, I get an x equals negative 3. Now we note that this has to be on the domain of negative 2 to 1, right? So if you have a different color pen or pencil, let's just indicate that we're knocking 2 of those candidates out because they don't fall within the domain, which I'm way fine with because it just helps create fewer candidates and a little less work. So I'm taking my endpoints and my one remaining critical point and doing a candidates test on them. Where do we go back to? Well, we go back to the original H that we're trying to find absolute max and mins for. Negative 2 squared would be 4. 4 over 1 is 4. 0 goes in, that gives me a 0 over 3, but that's 0. 1 goes in, that gives me a 1 over 4. I get a fourth. This is absolute max is 4 at x equals negative 2, right? It's so easy to read when it's organized. Absolute min is 0 at x equals 0. They really are not too bad to do. But I want you to see a graphing style one. In this case, we're given the function g is differentiable on the closed interval 0 to 6. So is my function continuous and a closed interval? Yes. EVT can be applied because I checked it out, because g of x is differentiable, which leads me to conclude it's continuous on, I'm going to indicate a closed interval just by writing the closed interval. So I know EVT applies. The graph g prime, the derivative of g, is given. Find the absolute extrema for the function, for the following functions. At which x does the graph of g have an absolute max value? Remember, we are looking at the derivative graph. So this is not the absolute max. It's the absolute max of g prime, but we're asking for the absolute max of g. So do I have any places? I'm going to kind of take the same approach. Are there any critical points? Well, that's where, not f, where g prime of x equals 0. My answer to this would be yes. Right here, right? That is where g prime of 4 equals 0. So x equals 4 is a critical point. And then we also have our endpoints. So my candidates list would include x equals 0, x equals 4, x equals 6. Well, before we went in and found y values, right? Not possible right now. So what are we going to do? we are going to use some logic, right? My G function, or what do I want to put? I want to put G prime right here. I'm going to do like a little sign chart. We got 4 here. If I look in this region, my derivative is all positive there, switching to negative. This is a relative max, isn't it? Do you suppose it's an absolute max? Yes, because G of x, this is important, let's use a new color. G of x is increasing to decreasing, isn't it? Oops, endpoints. Thus, x equals 4 must be the location for an absolute max. So how are we going to write that out? We put a lot of words and a lot of thought into this. Let's see if we can say it concisely. G has an absolute max. I can't say what it is, but I can say where it is, at x equals 4, because G of x increases from 0 to 4. I'm going to put the word on 0 to 4, and then decreases on 4 to 6. And that is enough to state that it's an absolute max. Example 5 is an E1. Would you like me to do that one? If you think you've got this, you could roll ahead and go to number 6. I will go ahead and do this. Let's get a k prime of x. That's going to be a cosine x times e to the sine x. A little chain rule, right? Derivative of sine gives us cosine. Now, this is multiplication. I'm going to indicate that with those parentheses. Let's set it equal to 0. 0 equals cosine x times e to the sine x. Well, from this, 0 equals cosine. I could get x is, where does cosine 0? Pi over 2 as well as 3 pi over 2. Can e to the sine x equal 0? Nope. None. No critical points coming from there. None critical points. It's not going to make sense English-wise, but we know what we're talking about there. All right, we got it. Let's create a candidates list. My endpoints, my critical points, because relatives can turn out to be globals. All right, taking them back into k of 0. E to the sine of 0 makes e to the 0 makes 1. You kind of dread e's and trig functions, but sometimes, honestly, they're easier. E, sine of pi over 2 is a 1. That just turns out to be e. K, which, if you don't know what e is, 2.718. K of 3 pi over 2, which is e to the sine of 3 pi over 2. That's an e to the negative 1. That's a 1 over e. 1 divided by 3-ish, about a 0.3, right? Keep that in your head so that we can judge which is biggest and which is littlest for y values. K of 2 pi, that's going to be an e to the sine of 2 pi. Well, that obviously is e to the 0, which is a 1. So we have absolute max is e, and that occurred at pi over 2. We have an absolute min, that's got to be right here, doesn't it? Absolute min is 1 over e at x equals 3 pi over 2. Not so bad. You dread them, but sometimes they're actually easier than the others. All right, let's keep rolling forward. I'm just going to clear some ink so that I don't use up so much memory space on my computer here. Example 6, find the min max value I'm sorry, velocity and acceleration. A particle moves along the straight line. What is s of t? That is position function, isn't it? Need to know that. And that gives us a polynomial for 0 to 3. So we have a closed interval. And this is a continuous function because all polynomials are continuous, right? They're beautiful functions, nice smooth curves. Find the min-max value of velocity of the particle on the interval 0 to 3. We want the min and max of velocity. Well, then I need a velocity function, so let's get it. V of t is coming off of an s prime of t, and that's going to be a 4t cubed minus 12t squared plus 12t minus 0. If I want the min and max of that function, I need its first derivative. So if I want to find critical points, I need to get v prime of t, which is going to be a 12t squared minus 12t plus 12. Factor out a 12, that's a t squared minus t plus 1. That is factorable. Oh, is it? Oh, I screwed up. 24, right? 2 times 12 is 24t. This is a 2t and it's minus. Got that? Make those little corrections because we factored out a 2 from the negative 24. That leaves us a negative 2t. And now, ladies and gentlemen, it is factorable. And I want to set that equal to 0, so I get solutions at t equals 1. I got a critical point at t equals 1. Now, I want to find mins and maxes. Guess what we go to? Candidates list. Write it out. It's worth points. You will get deducted on your test if you do not write it. Alrighty, so we've got t equals 0, t equals 1, t equals 3, nicely organized. We are talking about the min and max of velocity, so I need to look at the velocity y values. V of 0, V of 1, V of 3, V of 0. 0, 0, 0, oh, uh-oh. I just headed back to position function. That's not good. We come back to velocity function. 4 times 0 minus 12 times 0 plus 12 times 0. Looks like we get 0. 1, I'd have 4 minus 12 plus 12, getting us 4. 3 goes in. Ooh, that's going to be tougher. I should have an answer here. But I'm tired. It's 36. Got it. You can pick up where the max velocity, might as well make it applicable to the question asked, is 36, didn't give us any labels, so we won't include labels, is 36 at time equals, what was it? Time equals 3. Min velocity is 0 at t equals 0. Game done. All right, the last one. We are almost done with this. Find the min-max of acceleration. Well, in order to find the min and max of acceleration, I got to start with an acceleration function. And that acceleration function would be v prime, wouldn't it? So I've got a 12t squared minus 24t plus 12. There's a reason why I didn't grab the factored form of it. And that is because if I'm going to find min and max of acceleration, I need to go one more derivative, right? If I'm getting my critical points, that's going to come from a prime of t equals 0 or undefined. And I don't want to have factored form to take a derivative. That just forces me into product rule. So taking the derivative of a, I get 24t minus 24. That's easily factorable. 24 is a t minus 1. Set it equal to 0. T equals 1. Get a parenthesis there. T equals 1. I have a critical point. Guess what next? You probably know. Let's do a candidates list. You have done enough problems here today that you ought to have this down. T equals endpoint, T equal other endpoint, T equals critical values. Where are we taking this back to? Well, we want to know the max and min of acceleration, so it goes back into acceleration function. Taking it into acceleration, I'd have 0, 0, 12. Wouldn't I? 0 minus 0 plus 12 makes 12. 1 goes in. I'm going to have 12 minus 24, a plus a 12. I'm looking right here. 3 goes in. 3, 9, ooh, big numbers. Big numbers. Comes out with 48. Now, I think you can pick up what is the absolute. I love to draw borders and lines. Absolute max acceleration. Forgot what we were studying. Max acceleration is 48 at t equals 3. Min, or absolute min if you want to add the word, absolute min acceleration is 12. Happens at 2 spots. Oh, there should be a 0. What happened to me? I thought there was a 0 somewhere. This one, I never finished it. There's my bad. I was thinking I had 12s as answers. Okay, so it is 0. Sorry about that. It is 0 at x equals, at t equals 1. There we go, guys. Some very interesting problems. I wanted you to see those velocity acceleration ones at the end because people will mess those up because you do have to do a little bit of thinking. If I'm trying to find the min and max of a function, I need to take its derivative then of that function. So when they said acceleration, I had to start with acceleration, go into the next derivative, which is actually called jerk. Practice worksheet is all yours.